Good. Okay, thank you. So I'd like to thank organizers for this opportunity to give talk here. And I will be talking about bosonization, but in 3 dimensions and how it's related to AdS, CFT. And the talk is mostly based on the 2 papers. This one with Simone Jombi and Volodya Kirillin from Princeton, Vila Gurucharan and Sherman Prakash from the Alba Institute, and also a paper to appear with Ergin Sezgin and Yadong Zhu from Texas A&M. The main messages I would like to convey in my talk, and also the plan, is that in 3 dimensions there is an interesting class of conformal field theories that are called Chern-Simons meta-theories. So this theory is not only interesting because they capture some physics, but also because they of 3-dimensional bosonization. So the same physics can be described by a theory that is made out of bosonic matter. And the same physics can be described by another theory that is made out of fermionic matter. And there are also extensions of this bosonization duality that I think go under the name of web of dualities. So we'd like to study these theories and make some tests of bosonization conjecture, but the same results can be also interpreted as predictions for quantum higher spin theories. And this is the second part of my talk, because according to various conjectures, Chern-Simons meta-theories should be dual to higher spin theories in AdS 4, and we would like to reproduce some of the results in these Chern-Simons meta-theories from the higher spin side, as to make the story complete. And the first part is about Chern-Simons meta-theories. Chern-Simons meta-theories are interesting and challenging because the bosonization takes place in non-trivial interacting quantum field theories. But there are 2 degenerate points where everything collapses onto free theories. And this is a useful starting point because some of the properties that are easy to observe in free theories, they don't change considerably when interactions are turned on. So, and the simplest example of such a theory is just a free scalar field in 3 dimensions. But to be precise, we will need a free of into UN multiplet, because later in interacting theory, the main computational tool would be to use large expansion. And suppose that for some yet unknown reason, we're interested in UN singlet operators. So it is very easy to describe those. So you have obviously phi bar phi, scalar operator, then there is a current, there is a stress tensor, of course, but on top of those you have an infinite number of so-called higher spin currents. These are conserved tensors that you construct by sandwiching S derivatives in between 2 fields. Since the theory is a free one, conformal dimensions follow a very simple pattern. And, we know that stress tensor is exactly the current responsible for conformal symmetries. So likewise, higher spin currents are responsible for infinite dimensional extension of conformal symmetry, which is known as higher spin symmetry. And this is a signature of free theories in dimension greater than 2, because the opposite result is also true. So namely, if you find some conformal field theory in dimension greater than 2, and it has at least one higher spin conserved tensor, that you can bet that this CFT is a free one, which was proved by a number of people in various dimensions. So, okay, this is a very simple theory, and I added as a first theory to my diagram, which I will need to describe all these dualities and also AdS CFT correspondence. So another theory is more interesting. It's called critical boson, critical vector model, or Wilson-Fisher. It's IR, interacting fixed point under phi to the 4th deformation. And so it describes a lot of physics. For example, 3-dimensional Ising model is in the same universality class. But since the theory is non-trivial, interacting, it's hard to say anything exactly. And there are various methods like numerical bootstrap, famous 4 minus epsilon expansion, but we will use 1/n expansion for many reasons. So surprisingly, to the leading order in 1/n, there are not so many changes. So the dimension of the scalar operator jumps from 1 in free theory to 2 plus 1/n corrections. You still have a stress tensor, you have higher spin currents, but of course higher spin currents are no longer conserved. They develop small anomalous dimensions of order 1 over n. They're conserved. So higher spin symmetry here is broken by loops, but as I will explain later, it's broken in a very, it's only slightly broken, and it's broken in a very specific way so that you can take advantage of it and turn it into a very efficient computational tool. Oh, actually, I forgot to run this thing. Okay, so this is the second theory, and these two are related just by RG flow. So there is nothing. The third pure theory I need is free fermions. So it's also very simple theory, so psi d psi. So the spectrum of operators look almost the same. So the scalar operator has dimension 2 exactly. Then since this CFT is a free one, you have all the higher spin currents. So if you look at the spectrum, then it deceptively looks like the one of critical boson, but of course 1 over n corrections are missing. The CFT is a free one. And so this is the third pure theory I need. And the last theory is so-called critical fermion or Gros-Neveu. So here the story is sort of anti-parallel to what happens for boson. So you have UV fixed point, and again we can do large n expansion, and to the leading order what you find is that the dimension of the scalar operator jumps from 2 in free fermion to 1 in Gros-Neveu plus corrections. And of course higher spin currents also develop some 1 over n corrections. So higher spin symmetry is broken again. So now we have 4 theories, and in this pair and in this pair the spectrum of singlet operators look similar to each other, but clearly theories are different. So but what allows us to relate these theories is Chern-Simons. So there are many applications of Chern-Simons theory in 3 dimensions, but we will use it in the most canonical way just to gauge all the global symmetries we have in these theories. So it's topological field theory, therefore coupling something to Chern-Simons costs you no new local operators. So it breaks parity, so we expect our theories to break parity as well. And let's just do that. So we take all the 4 theories and add Chern-Simons term and covariantize derivatives. So now interacting theories have even more interactions, while those theories that were free now have interaction vertices, so they are not free anymore. And for this reason, the bosonization duality I'm going to describe should not look too surprising. Okay, so now we have, so in each of these theories we have 2 coupling constants. One is just n, the number of degrees of freedom, and there is another one which is Chern-Simons level. And as usual we combine them into sort of 't-Hooft coupling constant. So now from each of these theories you have a line of, so there emerges a line of theories out of each of these 4 points. And the conjecture is that not only this line ends on the critical fermion and say this line ends on the free fermion, but all the way from here to here you have 2 equivalent descriptions of the same physics. So that the Chern-Simons boson gives you the same observables as the critical fermion coupled to Chern-Simons upon appropriate identifications of these parameters n and 't-Hooft couplings, and likewise here. So this is the conjecture. Okay, so some general properties of these theories. So first of all, you can develop large n expansion for any 't-Hooft coupling, and indeed these theories turned out to be exactly solvable for all lambda at large n. So also we have interesting thing which are not supersymmetric CFTs with lines of fixed points. So the spectrum of singlet operators look the same, so you have higher spin currents with small anomalous dimensions in all 4 theories, while the dimension of the scalar operator can be either 1 or 2 plus corrections. So therefore they have approximate higher spin symmetry. Parity is broken in general, so they describe some physics, and what we going to study is the 3-dimensional bosonization and then relate everything to higher spin theories. So the observable we would like to compute are anomalous dimensions of higher spin currents. This is the one of the first quantum effects that you can, in principle, imagine in this theory. So higher spin currents are not conserved. There are some anomalous dimensions, but they are not conserved in this specific way, because in Chern-Simons meta theories you don't have too many operators. So if divergence of the current is not zero, it must be something, some operator in your theory, and there are not so many things you can write. Just by comparing quantum numbers, you see that in general there can be something bilinear in J and trilinear in J. So this formula is schematic. There can be derivatives, and of course currents carry some indices. But this is the general structure. So somehow higher spin currents are responsible for their own non-conservation. And all information is hidden in these numbers here, which are spin dependent and can depend on the coupling constant. And I would like to stress that in principle this is exact quantum equation of motion, which should be true even non-perturbatively. So there are numbers here which contain all information. So we'll fix the dependence on the 't Hooft coupling using results of Moldasen and Zhiboyedov, and later we will use some trick as to compute anomalous dimensions, and the trick will be to reduce everything to basically classical computation. What? So I mean, not in all four theories you can have. So you need this dimension 1 operator. So if it has dimension 2, for example, like in critical boson, then only these terms are possible. But if you have critical fermion, you can also add this scalar operator. So yeah, it not always happens, and it's actually suppressed. So we will not need these terms in our computation. Okay, so there are many consequences one can derive just from this simple equation. First of all, one can constrain 3-point correlation functions of higher spin currents. So in general, the thing is that in 3 dimensions, 3-point functions are not completely fixed by conformal symmetry. There are several independent structures that can occur. So one structure can in principle compute in free boson, another one is in free fermion, and another one is called odd. It doesn't occur in any of the free theories, and actually until recently it wasn't known how it looks like except for a few examples. So but this is the general structure, and in principle so this is JJJ, 3-point function of 3 higher spin currents. So you have 3 spins, and there in any realistic quantum field theory there should be some numbers here, some coefficients, and in principle you can have infinitely many of coefficients that depend on spins and whatever coupling constants in your theory. But everything boils down to just 2 phenomenological parameters if you use this equation. So it was shown by Moldasen and Zhiboyedov that if this is true, which is true in Chern-Simons meta theories, for example, then your 3-point function must have this simple form. So 't Hooft coupling appears only in the form of some cosine and sine functions using this relation, and already in this formula you can see the signs of bosonization, because this result is general. It doesn't rely on what the elementary constituents of your currents are. So you just assume this equation to be true, and then you get immediately, not immediately, but okay, after some computation, this formula. So for example, if theta is just 0, you have correlation functions like in free boson. As you depart from this free point, then there is a mixture of this odd structure and fermionic structure, and when you approach the opposite point, half, the situation is the opposite. You have a fermionic structure with a bit suppressed contribution of odd structure and bosonic one. And if you exactly at pi half, your correlation function look like those of free fermion. So, and again, I would like to stress that this result doesn't rely on whether your elementary constituents of these currents are fermions or bosons. Okay, so this is what we use to determine the dimension of these numbers on 't Hooft coupling, but using equations of motion and Chern-Simons meta theories, we can fix these numbers as functions of spins. And in principle, Chern-Simons met a well-defined quantum field theories, and we also did just the usual quantum computation in some of the cases. But I would like to describe another method that is based on multiplet recombination, because what this equation describes is how conserved currents, which are short representations of conformal algebra, recombine with some other operators as to form long representations of conformal algebra. And suppose we, for some reason, we know this non-conservation equation, that divergence of our current is something. In Chern-Simons method, it's just bilinear in the currents, but we don't have, to specify the structure for the method to work. So then 2-point functions are fixed by conformal symmetry to be simple functions of coordinates with some tensor indices, of course, of these currents. And then we can check conservation in two different ways. You can just differentiate this function, and then obviously the result must be proportional to anomalous dimension times another fixed function of space-time coordinates, because if anomalous dimension is 0, current is conserved, so this must be 0. But if you have some information about non-conservation of the current, you can just use it inside the correlation function, and then you find that anomalous dimension is proportional to this ratio of kk over jj. And the trick is that we gained one order in the coupling constant. So if you would like to compute anomalous dimension to, I don't know, 2 loops, then you need to know this result up to 1 loop. In particular, we're interested in 1 loop anomalous dimension, so it's enough to do this computation using just 3 weak contractions in the free theory, and then you get 1 loop result. So this turns out to be very efficient at 1 loop. Okay, so then after some computation, these are the results. So, these are typical crazy numbers that show up for anomalous dimensions. So lambda dependence is fixed. So you have 2 possible dependence on the 't coupling and 2 functions of spin, which are like that. So so there are many tests one can perform on these functions as to make sure that some general constraints are satisfied. But what is remarkable is that so we computed these functions in all 4 theories, and they are the same. So not only you confirm the bosonization duality, but also there is something that is shared by all 4 theories. Clearly they are different because here you have scalar operator of dimension 2, and here you have scalar operator of dimension 1. So there is, these theories are clearly different. But if you're just interested in anomalous dimensions of higher spin currents, then these functions are the same in all 4 theories. So which maybe still needs to be explained. And also there are some, for example, there are some properties that are to be expected. For example, at large spin, anomalous dimensions are proportional to logarithm of spin. This result can be interpreted as a quantum computation in the dual higher spin theory. And there are some other results that just go for a ride once you have this non-conservation equation in Chern-Simons meta theories. In particular, you can fix these odd terms which were not known. And the problem here is that in 3 dimensions, your 3 or higher order correlation functions can be arbitrary polynomials in 3 types of structures. So there is one structure that just contributes to 2-point function, so it carries 2 indices and depends on 2 points. There is another structure that depends on 3 points and 1 index attached to one of these points, and it shows up in the simplest 3-point function of 2 scalar operators with a tensor operator. And there is another one which is parity odd. It depends on 3 points and 2 tensorial indices. So and your 3-point function can be arbitrary polynomial in these types of structures. So, but using the equations of motion in Chern-Simons field theories, we fixed, for example, so we fixed these parity odd structures in Chern-Simons meta theories. For example, if you're interested in, say, stress tensor scalar spin 4 3-point function. This is how it looks like. This is just an example. So we know all of them, but just they are quite complicated, but this is like the simplest example. You see the odd structure and these Q's and P's. So this is what we would like to reproduce from higher spin gravity side. Yes, okay. So since Chern-Simons meta theories are well-defined conformal field theories, you can ask what kind of gravitational duals they have, and this can be answered, I mean, at least to the first approximation, by matching the spectrum. So we know the spectrum in Chern-Simons meta, and then of course the scalar operator is dual to scalar fields, spin 1 current to gauge fields, stress tensor to graviton, and then higher spin currents are dual to massless higher spin fields. So you should look for a theory whose spectrum is infinite and contains, say, every spin with multiplicity 1. That would be one of the simplest examples. And indeed, there are many conjectures that were put by people over the last years that Chern-Simons meta theories, or just vector models without Chern-Simons, should be dual to higher spin theories. And now we can add a third direction to this diagram. So I already removed this double line because we assume that three-dimensional bosonization is true, at least to this order. So and now each of these theories should have its gravitational dual. So for example, free boson, so the gravitational dual of free boson is called type A, and of free fermion type B. And actually the only difference between duals of these theories and of these theories is in the boundary conditions you can impose on the scalar field. So actually you should have just one theory that has two coupling constants, the gravitational coupling constant proportional to 1 over n, and additional coupling constant that is responsible for parity breaking. So and then the only difference is in the boundary conditions, and only at these 2 points, in type A and type B, you have parity. So this is the general picture. But okay, how these theories look like and what we can extract out of them in principle. So conformal field theories have been studied for ages, and there are many loops results available in many cases. But so this is not yet the case on the higher spin side, but there are some encouraging results. For example, many terms in the cubic action and some terms in the quartic action are known, and also recently Jombik, Libanov, Savdit, Seitlin, and many others, they computed one-loop corrections, which are vacuum bubbles, because the only information you need to compute those is the spectrum of your theory, and they work. But I mean okay, this is about action, but we know equations of motion in some form. So formally consistent equations are unfolded equations that are available either directly or we can extract them from Vasiliev equations, and they look like this just schematically. So you have two fields, so both taking values in the higher spin algebra. So there is one form here, and it contains its container for field bind, spin connection, and higher spin generalizations thereof. And there is a zero form that contains scalar, Maxwell tensor, Weyl tensor, and again higher spin generalizations. Higher spin algebra in 4 dimensions is exceptionally simple. So you just need functions of in 2 pairs of canonical operators. So if you know what 2-dimensional harmonic oscillator is, you can work with higher spin algebra in 4 dimensions. And this is what star is responsible for. So this is the product in the higher spin algebra. And there are other interaction terms which are not expressed in terms of higher spin algebra in any obvious way. Okay, so this is the general structure of the equations. And what we would like to compute are 3-level correlation functions, say 3-point functions. So it is clear that in order to extract AdS CFT 3-point functions, you can use just equations of motion, at least up to a number. So the unfolded equations are I mean, they contain a lot of auxiliary fields hidden in these master fields, but in principle, the field omega contains the Fronsdal field and derivatives of the Fronsdal field up to order S-1, while the C field contains derivatives of unbounded order of the Fronsdal field. And if you solve all these auxiliary fields, you end up with something like phi-cube theory to this order. So you have the wave operator, and there are some interactions on the right-hand side. And if you know this guy, you can either use it as an effective vertex in the action and plug in the boundary to bulk propagators, or you can try to solve equations directly and extract three-point function as the boundary limit of the solution. So this should give the same result according to all general arguments. And just to describe our results, I first need to go through what was already obtained. And there is, first of all, there was a remarkable paper that started the whole activity by John Bean. So basically, they took these terms, like commutator in the higher spin algebra, and extracted three-point functions with one scalar leg. They assumed that conformal structure comes out right, so it's enough to compare the prefactor. Also, they discovered something interesting, that these terms, they look strange, so they produce some results that naively diverge or inconsistent with CFT. Then later they used different method, in which space-time is sort of gauged away, and the computation is done in the tristorial space where higher spin algebra lives. And they again found that this thing is divergent, but they also found clever regularization such that three-point functions reproduce those in free boson or free fermion, complete three-point functions. But somehow this parity odd correlators that we need in Chern-Simons matter were found to be zero, at least in this computation. Later, using similar methods, we computed endpoint functions, but only in free series, but out of AdS CFT. So later, with these people, so we analyzed these CC terms and somehow discovered that too non-local to be treated by standard methods. And then Vasiliev came up with a clever non-local redefinition that puts everything into local form so that standard methods can be applied. So our goal is to take, say, this part of the equations of motion and extract everything we can extract, including the dependence on the 't Hooft coupling in Chern-Simons meta theory, and these pesky odd structures that now we can compare on the CFT side, because until recently we didn't know how they look like. Okay, so this is just the result of the computation. So in AdS, the computation is quite standard. If you know all interactions, you just use the inversion trick developed by Friedman and company, scalarize bulk integral, do it, and this is the result. So you have two possible boundary conditions that distinguish between this upper line in bosonization duality and lower line. So then there is a parameter theta that is related to 't Hooft coupling, and the dimension on this parameter comes out right. And also you can see four types of structures. These two can be found in free boson and free fermion, and are in principle known. For example, this is generating function in free boson theory. So these odd terms, they are a bit more complicated, but we managed to compute those and compare with the recent Chern-Simons matter computation we did with people. Okay, so everything works. In particular, this theta dependence results from, okay, it's maybe hard to explain, but at the free level there is some identification where some of the derivatives here are identified with derivatives of the Fronsdal field with some twist by this parameter theta, and this is how it enters the computation. And the very last thing we did, we took these equations after redefinition that makes them local, and also computed some of the correlation functions from the recent paper by Vasiliev, and they also agree with the AdS CFT correspondence. So now everything seems to work nicely. And coming to the summary, so we see that in 3 dimensions, there is a rich class of bosonic fermionic models called Chern-Simons meta-theories, and they exhibit Bose-Fermi duality, and we confirmed this duality based on anomalous dimension of higher spin currents. Also, we managed to compute 3-point functions. In particular, we fixed these odd terms that were not known. And these theories are AdS CFT dual to 4-dimensional higher spin theories that contain massless fields of all spins. And using these equations of motion, we reproduced 3-point functions in Chern-Simons matter. So we extended the tests done originally by John B. Yin to these parity odd cases, which now covers the full plane with these Chern-Simons meta theories. And also there is interesting indication that it's easy to see on the higher spin gravity side, but it results after very long computation on the CFT side. So it turns out that this parameter theta that is related to 't Hooft coupling enters Vasilyev equations in a very simple form. So basically through these cosines and sines. And this indicates that not only 3-point functions, as was shown by Maldacen and Zhiboedov, but all higher point functions in the planar limit should have this simple form of several structures with some cosines and sines. This is enormously hard to see in Chern-Simons meta theories, but it seems to follow in a very simple way from the higher spin side. So okay, I think I stop here. Thank you very much. Yes. So the problem was that they managed to reproduce the correlation functions in the 3 duals, which are like the opposite corners of this diagram. But then you have this theta dependence that, and this either did not come out right, or there was still some computation to be done. Actually, they indicated that in principle this theta dependence can emerge out of Vasilyev equations in the right form. But you need to compute actually to see if it's correct, which is easy to see. But what is not easy to see is that the structure comes out right, the conformal structure, because these structures that multiply this cosine and sine, they also represent correlation functions in critical boson and critical fermi. So they are not easy to compute in principle. But AdS CFT gives simple results. So we improved this along the theta dependence line, and also we added the correlation functions in critical boson and critical fermi.
Then the techniques are the same, so you are not changing the setup. So you just completed.
Techniques are absolutely standard. Okay. You just open Friedman Docker and
okay.
Yeah.
Do you have comments or ideas about the other topologies than the sphere? I suppose.
Okay, so I think the best we can get right now are these one loop determinants that we can compute. Actually, people in the audience did that. You can compute on various backgrounds, like thermal AdS, if this is what you mean. So and they do agree. So in the sense that you're not equating 0 to 0. For example, in the free duality, your CFT is free, and then the classical result must be correct. But then there are some non-trivial numbers that you can extract from loops, and they do agree. There's some highly non-trivial numbers that result from the higher spin computation of one loop determinants, and they do agree with some computation on the CFT side. But this is about vacuum bubbles.
Any other questions? Since we're there already, that was for S1 cross S2, but what about That was for S1 cross S2, but what about T3? or more complicated? Because it's kind of okay that it works in that case.
So you point into the problem of light states, right?
Yeah.
I mean, I think there are no new results in this direction. So I think so the safest claim would be that on simple backgrounds, higher spins should still be okay. But maybe on more complicated backgrounds, indeed, you have to add some other states to the theory.
Rather general question. If I understand well, the anomalous dimensions of those of the high spin currents are order 1/n.
Yes.
Finite.
Yes, in the large N expansion.
In the large N expansion, and that's also the loop expansion for the Vasiliev theory.
Right.
Does it mean that at tree level, the Vasiliev theory has always an exact high spin symmetry, and there is no way of having a classical, say, symmetry breaking?
Yeah, good point. So I think in general you're right that this the sub-leading 1/n correction should be matched with the loop computation on the higher spin side. But there is also something, there are some ways to break higher spin symmetry even classically, namely by boundary conditions. This was studied in some of the cases by Yin, Minvala, there's a paper ABJ triality. So you can indeed impose boundary conditions, and not all of them respect higher spin symmetry. For example, no, there is no simple example, but yes, they don't. So in this sense, the symmetry is broken already classically.
I think this is very well understood at the classical level. Let me give you a simple example. What people somehow unlucky call these broken higher spin symmetries is not breaking, is a deformation essentially. For instance, one can say that space-time symmetries at the same level are broken in general relativity, simply because Minkowski symmetry is broken in general relativity. So there are nonlinear corrections to all equations, including the conservation condition, essentially in this nonlinear deformation, which precisely correspond to those deformations in these equations. This is classical deformation of field equations, and it is very well known. This is precisely the cubic interactions that appear in these theories. Then, of course, one should consider quantum averaging of some composite operators to get anomalous dimension this way. So I think it's to a large extent a little bit misleading terminologies here on the breaking issue.
Yeah, I also agree that it's more like a deformation, because if it's just broken in a wild way, there is no, you can't extract any information, but it's broken or deformed in such a way that 3-point functions and perhaps higher order correlation functions are still constrained, because we can have infinitely many of parameters, but say Modasen and Zhiboyedov showed that no, sorry, there are only 2. And this exactly matches the Chern-Simons method story.
Any other questions? No?
Thank you.